is a true pleasure to introduce our first speaker. So we have today Shuran Song from Columbia University, and she's going to talk about hierarchical representations for language-based reasoning. Take it away.
Thank you for the introduction, and hello, everyone. Good morning. It is very early, but thank you for coming and be here today. So yeah, I'm going to talk about hierarchical representation for language-based reasoning. And I think my today's talk is actually really motivated by the questions of how to ground those powerful language models into the physical world so that it can be actually useful for robots. So let's start. So before, I want to start with this concept of a language as cognitive tools. I think long before the existence of large language model, there's many theories in cognitive development already hypothesize that although language is initially learned through and for communication, it is later internalized and used as a cognitive tool to organize our thoughts. Right, so in another word, our usage of language actually has becoming a very important and critical part of our ability to perform high-level reasoning and planning. And of course, with the introduction of large language model, we now have a very concrete way of implementing and validating this idea. Right? So recently, you probably see a lot of works in robotics that try to use make use of large language model to perform planning and reasonings for robots. And I think the most impressive part about all the systems is their flexibility in handling new tasks. As long as when the task can be described by a combination of some kind of objects that can be detected by the object detector and some actions that kind of come from a predefined or existing library of actions. So in some sense, this object detector or this kind of predefined action library has become the link that connects the large language models or the reasoning capability and the physical world that oftentimes is continuous, unstructured, and messy. Right? So, however, at the same time, we also observed that this object detector and predefined action library also become the bottleneck for a lot of the existing systems, like the language-based robotic systems. Right? So, for example, if your object detector is not expressive enough to describe some of those important object states, then the robot can, or the agent can easily miss very critical information to perform certain type of reasonings. Right? So, for example, knowing if an egg is not enough, you need to know like whether it is a full egg or a brick egg for some kind of planning task. And similarly, I think it's still very hard for today's language-based robot system to kind of acquire new manipulation or kind of just general low-level skills when the skill is outside the existing predefined library. So I guess that kind of observation is quite personally I feel it's nice because especially as a computer vision and robotics researcher, that kind of means that I can still keep my job for a while. So in today's talk, I'm gonna kind of focus on two of our very recent work. We just finished it and submitted, and we want to try to address this kind of very challenging grounding problem. We'll kind of give some examples of our attempts on addressing this problem. And one is actually focused on grounding in perception, like vision, and the other is focused on grounding on low-level robot actions. I think both of them are quite still one of the biggest challenges, in my opinion, on using language for robots. So we'll start with grounding in perception, and in particular, when we say that we want to ground language in perception, we kind of mean that we want to describe in language or in text what's going on in the physical world, and so that we can use to support large language model to perform reasonings on that kind of data format. And then we're going to study this question in the context of robot failure reasoning. Right? So we want the system to reason about when the robot failed and what caused the robot failure. So first, why we care about robot failure. Right? So I think with the increasing demand or expectations of asking our robot to perform harder and harder tasks, we kind of need to admit that failure is just inevitable, that will happen. And at the same time, I think kind of identifying the cause of failure oftentimes is quite tedious, and oftentimes it involves programmer or the engineer to read hours of robot log in order to identify what is the root cause of particular failure. And I think today's self-driving car can be a quite good example for this task, because even though we have thousands of cars deployed and collecting tons of data every day, in the end of the day, we still need someone sit in front of a computer, kind of reading through all the data and the log in order to identify the failures, and then like send it to the engineering team to fix it. So the question we want to answer in this project is that, can we develop the algorithm that's able to automatically detect and expand the failure types? Right, so basically, the input system will be the robot log data that includes the videos, the sensor input, and also the robot actions. And we want the system to kind of generate outputs that explains why the robot failed, what's the root cause, and at which time, right? So detecting the cause of failure and also localizing the failure time. So that's the task. So what does it take for a system to really able to expand a failure? So I think here are three basic requirements. First, the system needs to be able to explain or summarize what happened from the raw sensor input, and able to kind of identify what went wrong by performing some kind of long horizon reasoning. And then finally, also reason about what to do based on this kind of failure reasoning in order to hopefully correct the failure and then complete the task. And then among these three capabilities, actually the LLM can immediately help us on the later two by leveraging its like impressive common sense and reasoning skills. And I think the key remaining challenge is still really about how to generate an informative text-based summary from the raw sensor inputs of the robot so that large language model is able to directly reason about. Right, so that's also what I'm going to focus on talking about today, which is the first step. So what will make an informative robot summary for this kind of task? Right, so we kind of identified two important properties for robot summary. So first is that I think the summary need to be hierarchical, which means that the summary cannot just only have one level of abstraction, and oftentimes if you have different level abstractions, it's oftentimes very useful to support different levels of reasoning. So for example, higher level summary can oftentimes be useful to help to quickly identify the failure categories, like whether it is execution failure or high-level planning failure, whereas the lower level summary will provide details on the exact time and the spatial locations on the failure event, or so that it's actually those kind of detailed information is oftentimes more useful for the error correction. Right? So in order to perform this kind of reasoning, you really need different level of summary. And the second important property we found is that the summary also needs to be multi-model, means that it's able to take in all the possible sensor inputs the robot have in order to perform an informative, in order to generate an informative summary. And that is because certain type of failure or object states are just easier to detect from one type of sensor input than the other. So for example, to tell whether the water is running, it's just much easier to tell that from the sound information than from visual image data. And there are many other examples, like dropping an object is just so much easier to detect from the sound information. And those kind of sound information is directly lead to failures, right? So that's why it's very useful to include those multi-model or multi-sensory data. So based on that observation, we basically introduced and designed a hierarchical multi-sensory robot summary algorithm that's in the first level or the base level, we'll try to kind of summarize the sensor inputs that kind of describes those unstructured and multi-sensor data into a detailed test description that provides as many information as possible. So to do that, given our RGBD image, we'll first detect objects, and in particular, we're trying to detect task-relevant objects using open vocabulary object detector. And then for those detected objects, we'll try to extract their attributes by using a visual language model like CLIP. And then we'll extract their spatial information by using the depth information or like the 3D information. And all this information will be stored into a general 3D scene graph that can be kind of converted back and forth to a language description or a text description. And similarly, we'll also try to summarize the audio data by using a audio language model like audio clip into also a text format. And then in the second level, we'll try to condense this information like instead of summarizing every single frame, we try to select some keyframes based on certain critical events. Right? So for example, those events can be detected through changes in the scene graph as we just described, or audio events or robot events such as each of the end of the subtasks. And then in the highest level, we'll try to kind of further summarize this summary by using the sub-goal-based summary, right? So in that level, basically for each of the subtasks that's described in the robot's original plan, we'll try to summarize it by only describe the goal of this subtask and the final observation for this step, right? So I think one thing to note here is that this level of summary is oftentimes you will lose some important information, but it's also very useful for the reasoning module later to quickly narrow down the failure type and the steps. So that is why it's very useful. So with this kind of hierarchical summary that's condensed all the information in different abstraction level, we then designed a progressive failure reasoning module that basically systematically asks the LLM, like GPT, about what caused the failure and then expands the failure reason. So for this part, I won't provide much detail. So basically, the LLM is doing the heavy lifting for this kind of failure explanation and reasoning. But the one thing I want to point out is that by flexibly using different level of abstraction or summary, the system is able to identify different type of failures. For example, low-level execution failure, like objects dropped during certain steps, or high-level planning failures, like there's a missing step, for example, in the robot's original plan. And then with this failure explanation, we can then actually, again, prompt the LLM to provide a failure correction plan that basically generates steps for the robot to correct its action. And we can actually map the generated plan into robot's action and then execute those actions in the environment to potentially fix the error or correct its error. And then to evaluate the system, we actually introduced a new dataset. It's called a RoboFail dataset that contains the different scenarios of robot failure that's including both high-level planning failure and also low-level execution failure. And this dataset actually contains both real-world robot execution and also simulation environment in order to kind of evaluate different aspects of the algorithm. And then, for example, the real-world environment is more useful to kind of evaluate the perception module, whether they are good with real-world input data. And the simulation environment is very useful to evaluate the replan accuracy because the robot can actually execute the replan and then see whether it can complete the task afterwards. So here is actually a particular example in the dataset. So here the robot is actually doing the same task, which is boiling the water, but it actually failed on different aspects, right? So in the first example, the robot failed to boil the water because it dropped the pot at some point. And then in the second case, the robot failed to perform this task because it placed the wrong bowl to the stove. So the text here I'm showing is actually generated by the framework, and it expands the failure type and also localizes the time steps of where the failure happened. So that's the first part that we talked about how we can ground large language model in perception, basically how we can summarize a robot's multi-sensory experience so that we can support failure reasoning. And in the next part of my talk, we are going to talk about another aspect of grounding, that is grounding language models into robots' low-level actions or low-level manipulation skills. So here, what I mean by low-level manipulation skills, I kind of just thinking about it as acquiring fixed off closed-loop behaviors with high-rate controls. Right? So that's my definition, or at least in this context, definition of low-level manipulation skills. So this project, the title for this project is called Scaling Up and Distilling Down, Language-Guided Robot Skill Acquisition. So as indicated by the title of this project, it really has two parts to this system. So on the first part, we're trying to kind of scale up the data collection for the robot manipulation skills by using large language models and also simulation environments, which provide us those privileged state information. And then the second part is try to distill down those robot experience or robot data into a lightweight visual motor policy that we can actually eventually deploy it on the robot. So in the first part, scaling up part, we basically given any task you want the robot to perform, we use LM to recursively break down the task into smaller or like steps or like more executable steps. So this part is actually very similar to many of the existing works that's using large language model as planner for robots. But what's important difference here is that we will also allow the system to make use of sampling-based utility functions in order to kind of try to complete this task, right? So for example, we allow the large language model to also call either motion planning algorithms or graph sampling algorithms in order to perform those low-level executions. So one way to think about this kind of sampling-based utility functions is that by doing this sampling-based method, we actually introduce some kind of randomness to help the system to perform a little bit of low-level exploration in the low-level manipulation strategies. However, at the same time, the large language model helps us to decompose the task and therefore narrow down the whole search space and then enables more efficient exploration. And then finally, we can also ask LM to generate reward functions for each of the subtasks. So, and that can be used to help us to verify each of the subtasks, whether it is successful or not. Right? So here you can see that the large language model is actually generate a reward function that is rely on the state information of the simulator. That's why in the scaling up part, we actually need a simulator that we can easily get the state information. And then with this kind of reward function or the check function, we can actually ask the system to keep retries on a lower level until it's successful, right? So if the one task is not successful, it will just keep retrying before popping out to a higher level. So this kind of verify and retry mechanism really help us to improve the success rate in this data collection pipeline. And also it's introduced some important robust recovery behaviors, like basically showing the robot if you fail on certain action, how you can recover from that. And that is also very useful for the downstream policy learning. So now what we have will be a large number of multitask language-labeled robot datasets that we just collected with the method that we described. And then the next part, we're going to try to distill those experience or the data down into a language-conditioned visual motor policy. And so this step is actually very critical, and this part is actually not all the language-based robot system have, but I think it really addresses some of those common limitations of LLM-based robot policies. So for example, this step allows our system to kind of directly infer action from raw sensory inputs like images, instead of really rely on an external object detector or state estimator. Right? So this visual motor policy is something that you can directly deploy. And then second is that by using this distillation step, we allow the system to continuously improve its performance and its capability with more and more data or experience collected, either positive or negative, without the need to really fine-tune the large language model itself, which oftentimes can be quite expensive. So this distill down step is actually, I think, pretty critical to make the system or the policy useful. So in the end, we evaluate the framework with a large number of different tasks, like involve long horizon planning, common sense knowledge, tool use, and I think also intuitive physics. Right? So I think in the end, the overall performance is actually quite much better if we compare to those systems that directly use large language models as their policy. Right? For example, CODA's policy is one of the baseline that we compare to. And also the end system also inherits some very robust retrying behaviors from its training data that we see earlier. So to summarize, I think if we look at both projects at the same time, I think one thing that we can notice is that this kind of hierarchical representation is quite important and useful for grounding large language models or in general language models into the physical world. So for example, in the first case, we're trying to build this bottom-up summarization. And by using different abstraction levels, we allow the system to perform different levels of failure reasoning, such as planning failure or execution failures. And in the second example, we actually are performing this kind of hierarchy from a top-down perspective that we're trying to using a top-down decomposition of a certain task in order to enable efficient exploration by doing like verify and retry at each of the level so that the system can actually successfully collect training data for those long horizon tasks and don't suffer from those sparse reward problem. So I think in summary, I really think that this kind of hierarchical representation can be a pretty practical way of grounding those structured language models into our continuous and unstructured physical world, and therefore make them more useful for our robotic systems. And that's the end of my talk. Thank you.
Thank you so much, Shuran. We have time for questions. So let's see if there are questions from the audience.
So when you're trying to detect failures, at one point you said it was a long horizon kind of reason to figure out that there was failure. So is there an implicit assumption that because the reason why that failure happened originally was because the planning horizon wasn't long enough, or that there was some other reason? How do you balance those two?
Yeah, so I think when we were designing the algorithm, we try to not make assumptions about where the failure come from. So as we show in the data set, we actually consider both planning failures and execution failure. And it's actually quite important for the system to detect which level of failure it is. Right? So the way we're actually reasoning about the failure is that we'll kind of ask the LM to reason about each of the steps, whether they are successful. And then if one of the steps is not successful, then it's very likely to cause by low-level failures. And then if all the steps, if you just compare the sub-goal and the final state is successful, then the end task is still not successful, then very likely it's a planning failure that is caused by long horizon planning problem. So I think that is one way that we kind of try to handle both type of failures, and we try not to make assumptions about what is the typical cause of the failure. Yeah.
Thank you for the. Thank you for that talk. I'm interested in the false alarm for failure detection. Is this a problem, given that it's a learning-based failure detection? Thank you.
So the question is there false alarms in the failure detection algorithm, and is that a problem? I think it's actually very likely to be a problem, so there's nothing in our algorithm right now guarantee that is like how accurate whether it has false alarm or not. So it's just like any of the steps can have issues. For example, if your perception algorithm, like the summarization steps, has a certain error, then it's very likely that the failure reasoning won't work because of the summary itself is wrong. So I think that's a very interesting problem that I don't think we fully address that. So right now, the way you can think about how to use it is that you have all the robot log data, all the videos, you plug it into the framework, and it will try to provide some explanation. Maybe some human need to kind of come in and check each of the failure explanations and see whether that makes sense. And then, so we still need a verification step in the end to guarantee that all the failure detected is actually correct. Yeah, so our evaluation does track that. So we evaluate the accuracy of the detected failure steps. But yeah, the performance is not 100%. Yeah.
Hi, I had a question about the scaling up and distilling down. So I know in scaling up, you're recording successes and failures into the robot experience. Yes. Are you able to use those failures to help teach the visual motor policy what not to do, or are you just training on the successes?
Yeah, so that's a very, very good question. So the question is, when in the scaling up part, we're actually collecting data with both positive and negative data. And the question is that in the distilling part, do we train on both positive and negative data? That's actually an experiment that we did in our project. So you can think about the simplest way is just you only use the positive data. That's kind of train a behavior cloning method that's only learn from the positive data. But I think intuitively, we found that, we think that it should be also very beneficial to also learn from the negative data to know what cannot do. And I think that is actually true, but oftentimes it may limit it by the learning method that you use. Maybe they are not very well suited to learn from the negative data. But from what we experienced is that oftentimes sometimes it helps, sometimes it doesn't. And the cases when it helps is that it helps for generalization, right? So knowing the negative data actually really helps them to kind of learn the general concept of how to do a task. But if you're just overfitting the positive data, it actually oftentimes gives a better performance on that particular task itself. So if we just only evaluate on performing that exact task, learning from positive data is enough. But you hope that the system can generalize, for example, to new objects, then learning from negative data is also very important.
Thank you.
Thank you. Thanks for your very nice presentation. And my question is like, okay, so like in the first hierarchical representation, that project, you proposed like a very natural and good representation, like language-based representation for the robot task. And in the second task, you also mentioned like there are some like recovery behaviors from your models. But like, have you ever tried, like use the automatically generated like failure logs from the first project to do some recovery behavior?
Yeah, so the question is that have we tried to use the first work that summarize the failure and then use it to improve the second work? We haven't, but I think that's a very interesting idea. I think the one limitation or one issue that we need to fix in order to really get there is that our first project is kind of, we assume that it's offline processing. So it means that we have all the data already, and then we try to generate a failure summary. But in the second case, we kind of need more online failure detection, right? You need to immediately know whether the task can be proceeded at that step. So there is a little bit of mismatch in terms of the method for it to actually immediately be used. So I think we probably need to make an online version that's able to immediately tell that's what failure happened instead of going through the whole video in order to kind of quickly provide feedback for the second project.
Hi, yeah, thank you for the great talk. My question is regarding your first work on failure explanation. And I'm wondering how, related to the first question, how you capture long-term failures that are potentially ambiguous. For example, a robot getting caught on a hook. So when you're planning, during the planning, you don't actually know what step you plan to enter the hook. So it could be a very long horizon attribution error task. So do you have some kind of mechanism for capturing ambiguity as to what part caused the failure?
Yeah, so the question is that whether our, it's about the first project, whether our framework is able to handle or kind of design anything to handle these ambiguities of failure. That's actually something that we encountered quite a lot when we are working on this project, because there is actually quite a lot of ambiguities in determining what is the root cause for failure. And oftentimes, if you really look at the failure case in robot execution, it's a little bit hard to determine what is the root cause. Sometimes you can say it's because the plan is not robust enough. Sometimes you can say that because the execution is not robust enough. And maybe if you fix one of them, you can fix the whole pipeline. So I would say that that's still something that's, I think, open question for this task of failure explanation. We tried a little bit in our problem formulation that we try to categorize the failure types, and we also manually defined what we think, as a human looking at the execution, is a root cause of failure, and we kind of categorize the steps and also the type, and then use that for evaluation. But I don't think we have a really good way to, for example, generating multiple explanations that it can cause by multiple levels of issues. I think that's maybe one possible solution for these ambiguities.
Okay, yeah, thank you for the response.
Yep, maybe while we wait for more questions. Sorry, we have extra time, so we'll grill you for another 3 minutes or so. The hierarchical summarization part is supervised, so you have to supervise the sub-goal detection and the key.
Yeah, so the question is that for the hierarchical summarization for the first project, is that supervised? So actually, it is not supervised, it's zero shot. So the object detector itself is supervised and trained, and the visual language model, those components are self-supervised, not self-supervised, they are supervised. And then, but when we use it, actually everything is zero-shot. We just run the object detector and summarize in text. So the way that we summarize is we kind of use different modules to ask for different questions, and then and take those questions and summarize those objects and object states into text. And then to condense that information is actually we just either prompt the LM to provide more summary. We design certain heuristic rules to summarize those information. And yeah, detecting the sub-goals, for example, that's actually come from the robot plan itself. So the robot originally has a plan, and we use that to summarize the sub-goals.
Very nice. Okay. Last one, unless there is more. I want to connect to the first question and also the last one about the failure modes of the failure detection part. So do you have examples of the way the framework fails to explain the failures, or do you have maybe you had an assessment of the success rate of the failure detection? Can you say a bit more about when it works? What does in case of failure?
Yeah. So I have to say that there's still a long way to go. As far as I remember, the success rate of detection is around 60 or 70%. Is that there is still a lot of cases that actually cannot correctly detect the failure cause. And I would say that the typical failure type that we found really hard to detect is actually the low-level execution failures, because it actually requires more detailed understanding about the sensory input data. Because the planning failure, at least the way that we construct the data set, if it's a planning failure, and oftentimes the system only need to reason about the plan itself and the final state of the robot or the task, it doesn't really need to go through each of the steps and figure out which step what goes wrong. So I think the execution failure in general, in our experience, is harder to detect.
Shuran, thanks so much for the patience, for the many answers. Let's thank Shuran again.
Thank you.